We said we can't place the complex numbers on the number line, other than the real numbers, of course, real number line. So we have a different picture to try and visualise all the other complex numbers. It's known as the Argand diagram. It looks surprisingly familiar. And so the idea they came up with, let's come up with an imaginary number line, and we'll just place it perpendicular to the real number line going through 0. All of the imaginary numbers would be on the imaginary number line, all the real numbers will be on the real number line, and the mixtures will just be out in space somewhere. So that becomes our real axis, and that becomes our imaginary axis. And sometimes you'll even see them labelled as, instead of X and Y, you'll see it labelled as real and imaginary. So all right, the real number 2, not a problem. Let's go and place it on the real axis. There it is. The imaginary number, minus 3i, again, not a problem. There it is. But then we get a mixture. Minus 2 plus I, well, it's just like coordinate geometry. Minus 2 becomes the x value, if you like, and I becomes the y value. And so that's where we'll plot C. So 4 minus I, 4 is the real bit, negative 1's the imaginary bit, there's D. 4 plus I, 4 is still real, but now the imaginary part's positive 1. Now this brings up an interesting point about when we're visualising complex numbers. D and E are of course conjugates, but what we should see is conjugates will always be a reflection in the real axis, because the real part's always going to be the same. It's just the sign's changing on the imaginary part. So what about if we had the complete negative of it? So minus 4 plus I, there it is over there, well that one turns out to be a reflection through the origin. So if we multiply by negative 1, we reflect through the origin. This becomes an important feature that we'll be using a bit. The multiplication by I. If I was to multiply by I get 1 plus 4i, and there it is up there. It turns out to be a rotation of 90 degrees. So every time you multiply by I, it rotates 90 degrees. So when you multiply by negative 1, remember, we rotated 180 degrees. 90 plus 90. So every rotation of I is a 90 degree rotation of our complex number. And obviously, because we're talking about a number plane, there's going to be a unique position for every single complex number. So there's a spot for all of them. So we're going to have a look at this idea of locus in terms of complex numbers. So horizontal and vertical lines, for instance. If I had a horizontal line, well, when we're talking about coordinate geometry, we'd say, oh, that's y equals c. But now if we're saying, hey, I'm going to plot every single possible complex number that I can that would lie on this line, what do they all have in common? Well, they all have an imaginary part of C. So that would be a way of expressing that line. And a vertical line would see a very similar thing. All of the complex numbers that are plotted along that line would have the same real part. So that could be the real part is equal to, well, in this case, K. Circles, there's a circle. Now, in coordinate geometry, we'd say x squared plus y squared is equal to r squared. We saw yesterday, remember, a number times its conjugate is x squared plus y squared. So instead of saying x squared plus y squared is equal to the radius squared, we could say a number times its conjugate is equal to r squared. So if we plot every complex number such that when we multiply a number times its conjugate and we get r squared, we would end up with a circle radius r. So all right, let's try some of this. Find and describe these loci. Z plus 4 plus I, mod z plus 4 minus I equals 49. Now, if we don't recognise it straight away, let's turn it into coordinate geometry. If I play with the conjugates first and expand out, I'll get z times z conjugate, 4 plus I z, 4 minus I z, 4 plus I, 4 minus I equals 49. Eventually, right, so z conjugate you can see becomes x squared plus y squared. The z plus z conjugate, well that's going to be twice the real part. Because if you add a number with its conjugate, the imaginary part cancels. So I end up replacing that with 2x, so we get 8x. Now this one here, the imaginary part, imaginary times z plus z conjugate. So now we'll end up with 2y. And then 4 plus I, 4 minus I, difference of 2 squares, which becomes the sum of 2 squares, 16 plus 1. We've now got something that hopefully we recognise to be a circle, because you will notice the power of x and y is 2 in both. And if I tidy all that up, so we want to complete the square on the x's, complete the square on the y's, and there it is. X plus 4 squared plus y plus 1 squared is 49. So we've got a circle, centre minus 4 minus 1, radius of 7. So I think you'll agree with me that, geez, that was a bit of a pain expanding that whole thing out. But there actually is something we can look at here to tell straight away, and really it's like shifting. We know z times z conjugate was a circle. So if I go z minus a complex number, and then the conjugate minus the conjugate of that complex number, it's like I've just shifted that circle, whatever that complex number is, omega. So had I seen it from the first line, I say, oh, hang on, this is z minus -4, -1, or negative I, and here's the conjugate minus the conjugate of that. Then straight away, because, oh, hang on, that tells me the centre is going to be -4, -1. So if you spot that, you can save yourself a lot of working out there. Ooh, here's one where, just by looking at it, no. So the reciprocal of z plus the reciprocal of the conjugate, again, don't recognise it straight away, so let's play with it. I'm going to multiply, getting rid of the fractions basically, multiply, and so I'll get conjugate plus z is equal to z conjugate. Now I can sub in the x and y's and come up with some sort of an equation. Well, a number plus its conjugate will be twice the real, so 2x. And a number times its conjugate will be x squared plus y squared. So actually we've ended up with a circle again. So x squared minus 2x plus y squared is equal to 0. X minus 1 all squared, when I complete the square, plus y squared is 1. So it looks like we've got a circle, centre 1, 0, radius 1. There it is. Only problem is that's not the answer. It's the answer to the new thing that I've created. Remember, we're saying these are all the numbers that would satisfy 1 over z plus 1 over z conjugate is equal to 1. Slight problem though. What's my problem? Yeah, so what's our problem with fractions? Can't have 0 on the bottom of a fraction. Can't have any number over 0 for that matter. So, hang on, it would not be possible for z to equal 0. So there's an exclusion just at that point. Otherwise, yes, it'll be the circle. So always, again, refer back to the original one and go, hey, oh, hang on, is there anything fancy happening here? So let's have a bit of a play with locus.